Section 25.3. Combinations of capacitors. We will begin by familiarizing ourselves with standard circuit symbols and diagrams used to represent electrical components. Following this, we will explore how to analyze capacitors connected in parallel configurations. Then, we will examine capacitors connected in series configurations. Finally, we will learn a step-by-step method for reducing complex circuits into simpler equivalent circuits to determine their overall capacitance. In studying electric circuits, we use simplified pictorial representations called circuit diagrams. These diagrams use specific symbols for various elements connected by conducting wires. The symbol for a capacitor consists of two parallel lines of equal length, which represents the geometry of a parallel plate capacitor. A battery is represented by two parallel lines of unequal length. The longer line represents the positive terminal, which is at a higher electric potential, and the shorter line represents the negative terminal. Finally, a switch represents an electrical connection. When the switch is closed, it allows a connection between the components, and when open, it indicates a disconnection in the circuit. Let us look at two capacitors connected in a parallel combination. When capacitors are in parallel, the individual potential differences across each capacitor are exactly the same. This means the voltage drop across capacitor 1 equals the voltage drop across capacitor 2, which equals the total applied voltage from the battery. After the battery is connected, the total charge stored by the combination is simply the sum of the charges on the individual capacitors. We can express the total charge as charge 1 plus charge 2, which is also equal to the capacitance of 1 times the voltage plus the capacitance of 2 times the voltage. This allows us to define an equivalent capacitance for the parallel setup. We can simplify the parallel circuit by replacing the individual capacitors with a single equivalent capacitor. This equivalent capacitor must store the same total charge at the same applied voltage. Using our charge equation, the equivalent capacitance times the voltage equals the sum of each individual capacitance times the voltage. Because the voltages are identical, they cancel out. For any number of capacitors in parallel, the equivalent capacitance is simply the algebraic sum of the individual capacitances. Remember that this equivalent capacitance is always greater than any individual capacitance in the parallel group, because combining them effectively increases the total plate area available for storing charge. Now we consider a series combination of capacitors. In a series combination, the charges on all the capacitors are identical. The charge on capacitor 1 equals the charge on capacitor 2, which we can just call the total charge. This happens because the inner plates form an isolated system that must maintain a net charge of 0. However, the total voltage across the entire series combination is the sum of the individual potential differences across each capacitor. So, the total applied voltage equals the voltage drop across the first capacitor plus the voltage drop across the second capacitor. This relationship is key to finding the equivalent capacitance for a series circuit. Let us derive the equivalent capacitance for a series combination. By applying the definition of capacitance, we substitute voltage with charge divided by capacitance into our voltage sum. This gives us the total charge divided by the equivalent capacitance equals the total charge divided by capacitance 1 plus the total charge divided by capacitance 2. Since the charges are identical, we divide them out. We find that for any number of capacitors in series, the inverse of the equivalent capacitance is the sum of the inverses of the individual capacitances. As a result, the equivalent capacitance of a series combination is always less than any individual capacitance in that combination. We will now look at a practical example of circuit reduction. Complex circuits can be simplified step by step by identifying local parallel and series groupings. Looking at the diagram, our first step is to combine the top parallel cluster consisting of the 1.0 microfarad and 3.0 microfarad capacitors. Adding these together gives an equivalent capacitance of 4.0 microfarads. In the second step, we look at the bottom parallel cluster. We add the 2.0 microfarad and 6.0 microfarad capacitors to get an equivalent capacitance of 8.0 microfarads. We systematically redraw the circuit after each reduction. Continuing with our circuit reduction, the third step addresses the newly formed top branch. We now have two 4.0 microfarad capacitors in series. Using the inverse sum rule, 1/4 plus 1/4 equals 2/4, which gives an equivalent capacitance of 2.0 microfarads. In the fourth step, the bottom branch has two 8.0 microfarad capacitors in series. The inverse sum rule here yields an equivalent capacitance of 4.0 microfarads. In our final step, we are left with a simple parallel combination of the 2.0 microfarad and 4.0 microfarad equivalent capacitors. Adding them directly gives our final total equivalent capacitance of 6.0 microfarads. Let us summarize what we have covered. For parallel combinations, the voltages across the capacitors are identical, and the total equivalent capacitance is found by adding the individual capacitances directly. For series combinations, the charges stored on the capacitors are identical, and the equivalent capacitance is found by adding the inverses of the individual capacitances. In circuit analysis, you can simplify complex networks by finding local series or parallel clusters and replacing them with equivalent capacitors. Physically, you can intuitively think of a parallel connection as effectively increasing the total plate area, and a series connection as effectively increasing the separation distance between the plates. To wrap up this section, consider these two review questions to test your understanding. First, if you have two identical capacitors, which connection type, series or parallel, will result in the highest total stored charge for a given battery voltage? Think about how equivalent capacitance behaves in each case. Second, why must the net charge on the isolated middle plates of a series combination remain zero if they were initially uncharged? Consider the physical connections and the principle of conservation of charge. Reviewing these concepts will solidify your understanding of capacitor combinations